In this section, we are going to consider how delta G, or Gibbs free energy, changes are related to reactions that are in equilibrium. So in this section termed equilibria and the relation to delta G, we're going to start with this energy diagram here. So we're going to consider this figure, and you see that we have our two reactants, A and B, which turn into C and D. Right, so we have our reactants A and B, our products C and D. But you might notice here that there's a reversible arrow. This indicates that we have a reaction in equilibrium. So we're told that this is an exergonic process, right? So we have a negative delta G. So we have products that are favored. And we notice this with the lower energy of C and D here. Right, so that's where this negative delta G derives from. And in the forward direction, we would say that this reaction is spontaneous in the forward direction, right, with a negative delta G. But what happens is that the forward and the reverse of this reaction actually eventually will reach the same rate. Right? So we'll obtain this equilibrium where both the forward and the reverse reactions are occurring at the same time, at the same rate. So a spontaneous process overall would mean that there will be more products in the end than reactants. So we'll look at this relationship in the next slide, actually. But first, we'll consider why doesn't the reaction just go in one direction, right? Why doesn't it convert all of A and B into C and D? So we can rationalize this in the sense that as the concentration of our reactants, A and B, decreases, right? So that goes down, the number of collisions between the molecule, A and B, the reactant A and B, will also go down. So because of this frequency, we're not going to make as much C and D product. And at the same time, the concentrations of C and D will increase, right? We're creating product because we just started with reactant in this scenario. So we're increasing C and D, therefore increasing the number of collisions, and then that would produce more of A and B, right? So we're in this kind of cycle that occurs. A and B increases the concentration of C and D. As C and D increases, then the concentration of A and B will rise then at that point. So eventually, right, the forward and the reverse reaction rates will be equal. So this is the first time we mention the term of rate. And when we consider this equilibrium constant that you may remember from, again, a previous term, when you discuss thermodynamics, this equilibrium constant is a ratio of the concentration of products to the concentration of reactants. So this tells us exactly how much magnitude-wise or quantity-wise we have in this relationship at equilibrium of products to reactants, right? So we see this relationship here, right, with equilibrium constant. There's also an equation listed here that relates delta G to the equilibrium constant. So this was used again back in general chemistry 2 when we did some thermodynamic calculations for delta G. But this semester, we really want to just focus on the fact that KEQ, Gibbs, enthalpy, entropy, these are all thermodynamic terms. And these really only describe the relative stability, right? How stable our products and reactants are, and then the ratio in which they're formed once they reach equilibrium.